Okay, so we have seen the definitions of a global minimizer as well as a local minimizer. So now we are going to find what are the properties these minimizer points satisfy. When we say the properties, what are the conditions these properties satisfy? And when we go to the conditions, what are the necessary conditions and what are the sufficient conditions of these points? So that we can identify, we can actually obtain this minimizer points or the maximizer points. So as we have talked earlier, as we have discussed earlier, in this particular course, we'll be more focused on minimization of functions. So we'll be more interested in minimizer points. Okay. So how do we find minimizer? So that is an important question here. Let's see. How to find minimizer. Okay. So one thing which we know, we have to notice, if x star is a minimizer or maximizer, the maximizer condition we are not looking at this point of a function f of x, of a function f of x, okay, then f of x star is equal to, f dash of x star at that particular point. That means the derivative of that function, or a better way to write this is at, if you take the derivative of function and put x is equal to x star, that will be 0. Okay, so um, what is it? What does it mean by this condition? Let's look at the graphical point of view. Okay, we have a function. We assuming that x star is a x star is a minimum point of that function. So in 1D, it's easy to mean. What does derivative of a particular point in 1D mean? It is a, yeah, in any sense, it is a slope of the point, right? So at this minimum point, we've seen that the slope has become, or the derivative, so derivative is the tangent to that point, and the slope of the derivative, slope of the tangent is, so okay, let's write this down. Derivative of a function f of x at a point x star is the slope of the tangent to the function at x is equal to x star. So I hope everybody know what the tangent is. So at that particular point, this is a tangent. At this point, this is the tangent. At this point, this is the tangent. So here it is a tangent. Yeah, it's a tangent to a particular curve. So at any kind of, at a minimum point or a maximum point, wherever there is a change. So what the key idea is, so if you look at left side of this point, its slope keeps on decreasing, and then it is increasing at the other end, right? Here the slope is negative and here the slope is positive. So when the slope is changing from positive to negative, at one point it has to be 0. That is a key idea, and that is the minimum point of the function. Okay, so the slope of that particular point is slope of the tangent at that particular point is 0 if that point is a minimizer. Then one question which is important to ask here is this necessary or sufficient condition for minima, or let's call it minimizer. So this is an important question. So when we say the derivative of that function at a particular point is equal to 0, is it a necessary condition or is it a sufficient condition? So what I'll just recap of what give a recap of what is a necessary condition. So by necessary condition, what we mean, so here we have the condition, right? The condition we have here is f dash at x star is equal to 0. If that by this, just by this condition, we can say it is a minimum. Then we call it a sufficient condition. If by this condition we can say it is one of the conditions to be a minimum, then this is actually a necessary condition. It happens that this is actually not a sufficient condition, this is a necessary condition, because the answer lies here. See, the answer lies here. We are looking for a condition for a minimum, right? We are trying to minimize a function. So there are two set of points, not just two. There are different set of points at which this condition is being satisfied. It could be a minimizer, it could be a maximizer, it could also be a point where it is not a maxima or a minima. It depends on the nature of the function also. So just by saying that slope of the tangent at a particular point is 0, or the derivative of the function at that point is 0, doesn't imply that it's a minima. But how does a necessary condition work? If we try to take the contrapositive of that statement, here we say derivative minima implies derivative is equal to 0. So that is a necessary condition. So derivative not equal to 0, not a minimum. So whenever we say it is a minima, that is sufficient for the fact that the derivative of that particular point is 0. Okay, I hope it is clear to you. It is it's not that tricky, but let's understand this is a necessary condition. So if you want to have further grasp on, or if you have confusion on necessary and sufficient conditions, you can refer back to my lecture on necessary and sufficient conditions. I'll do a separate lecture on necessary and sufficient conditions to understand the logic of it. So just understand this is a necessary condition. And one important thing which you have to notice, necessary condition, so derivative, if you take all the points, all points with f dash of x is equal to 0, and all minima, let's take local minima, minimizes, what we can say, yeah, let's consider this as a set, or a better way to write this is, let's say x is a set where where f of x is equal to 0, and x is a set where x is a minimizer. What will be the relationship of these sets since it is satisfying necessary condition? It could be like this is the point of minimizes, the set of minimizes will be always a subset, an improper subset of, could be equal, but always not, always keep in mind that this is a bigger set and this is a smaller set. So if we take this as set A and set B, there is a possibility that both could be equal, depends on the function, but there is not a possibility that it's always equal. So that's what the necessary conditions. Okay. Okay. So so what has happened here? We had a set of points. We had all x's, right? All x's. X belongs to R. So from there, we have actually scaled it down to a set of all x's such that f of x is equal to 0. But the issue here is it has minimizers, maximizers, not minimum, maxima, all this thing. So we have done a certain level of zooming in, or what do you call it, cutting down, uh, yeah, closing in to this. But that is not enough. We have to further close in so that we ultimately land at a local minimizer. So for that, we use the second order condition. Second order condition. So what does the second order condition say? If the first condition is satisfied, something which is already provided, then the second derivative at x equal to x star, that is d square d by dx square of f of x at x is equal to x star, if this value is greater than 0, it is a minimizer. Okay. Uh, so what? So let's try to understand this. So we had all the set of points, which we had all the points which is in the domain of a particular function f of x. We're trying to find out which are the minimizer points. So we have further narrowed it down to a set of the set of points where the first derivative of that function is 0, right? This is the first order conditions, right? Now we are scaling it down. Now we have already narrowed it down. Now we are again saying out of these points, which of the points satisfy f of x is uh, greater than 0. Then such points is finally the set of minimizes. It could be a single point, could be multiple point. That is another point of discussion here. So right, this is the minimizer. So we are that's how the progress goes, how to find a minimizer. Okay, so we have a first order condition, which is a necessary condition. What about this condition? Is this condition necessary or sufficient? So what we should understand is, suppose we just have um, a function f of x. We skip the first condition. We're not looking for the necessary condition. We just go for the second derivative test. Okay, second we are calculating the second derivative of that function, and we are putting x is equal to x star and see whether this is greater than 0. Is this sufficient? Yes. It turns out that it is sufficient. So we have uh, what do you call? We have a set of points here. So whenever this condition is satisfied, we can say that it is a minimum for sure. It is not like it. It um, could be a maxima. No, it could be neither maxima nor minima. It could be a saddle point. No, this condition is satisfied only by the points which are minima. But there's one important thing here. And the important thing to note here is that just by checking second order conditions will not generate all the minimum points. Minimum points, okay? Minimum points. Because sometimes the second order derivative may fail. It may this condition may fail, but still that point could be a minima, right? So just by employing this condition, or even when we are applying the first and second condition together, we can't be sure that we may find a minimum of that point. So this is uh, just like saying this is a sufficient condition. For example, uh, being a square, okay, we have a polynomial which is a square, okay, that square, being a square is sufficient to say it's sufficient condition for being a rectangle. So if we have given that it is a square, then we can say it is a rectangle. But is it does it contain all the set of rectangles? So is being a square the only way of being a rectangle? No, right? So we're missing something here. There could be rectangles which are not squares. How do we find those rectangles? That is a similar thing. So let's take an example to understand this more clearly. For example, uh, let's consider the function f of x is equal to x square, right? So how do we proceed? We have the first order conditions. We take the derivative and put it equal to 0. So it will be like 2x is equal to 0, x is equal to 0, right? Now the second order condition check is f dash of 0. We put it so this is actually our x star. The second order condition is we take the second derivative, put that should be greater than 0. But here, what is f double dash? Here, f double dash of x is equal to 2. When you put that x equal to 0, it takes again 2, which is greater than 1. So this condition is satisfied. Okay. So this works for f of x equal to x squared. Now, let's take the example of f of x is equal to x raised to 4. This is also a similar function which has a similar shape, and we know the minimum of this function from the graph of the function. We know it exists at x is equal to 0. Okay, but what about the tests here? The first order conditions, when we put it f of x is equal to 0, it gives 3 into x cube is equal to 0, or x equal to 0. That is fine. And then we go with the second order conditions. Second order condition says, uh, what is the second derivative? 9 x square, if I'm not wrong. Sorry, this is not 3. So it is actually is the second derivative of x, and when we put that at x is equal to 0, it becomes 0, which does not satisfy the condition for a second. This will satisfy the second order condition. It does not satisfy the second order condition, but there's a minimum. So we are missing this minimum when we're doing this check. Okay. So second order condition is something can be done to find the minimizer of certain functions, but there is definitely a failure for second order conditions. We may miss some points. So we call the second order condition as a sufficient condition. Okay. Now we will state these conditions more systematically in the coming lecture, and we'll state this as first order necessity conditions, second order necessary conditions, and second order sufficient conditions, which we'll see in the next lecture.